Okay, so one of your kind classmates has brought a thermoelectric device. So in this case, you apply a voltage to the device and it sucks heat out, it makes one side hot and the other side cold. In principle, you can reverse it. Doesn't mean it has the same efficiency if you reverse it, where you would apply a heat source on one side and a heat sink on the other, and that temperature difference would charge the battery. Okay? So I'm going to pass this around, and you can feel one side getting cold and the other side getting hot, so everybody just kind of look at it. So this comes up where we were talking about, violations of the second law, and then I said, well, so you can't give heat to a circuit to get current flow. Well, so I can't apply heat to this to charge the battery. But yes, you can if you apply heat and remove heat. So you remember the Kelvin Planck statement? So just pass this around. You can't just by purely adding heat do work. You have to remove heat and add heat. Okay, so we'll move on more towards lecture material. Last lecture, we talked about these TDS relationships, and we had first and second TDS relation. I derived those for you. Then we looked at, entropy change of liquids and solids. And we had, expressions for the first and second TDS relationship, and then the entropy change for an ideal gas. So we have the ideal gas expression up at top, and then we have the first TDS relation, second TDS relation, and we end up getting the change in entropy of my system, which is an ideal gas. Okay, my system's an ideal gas. The change in entropy of my ideal gas using the first TDS relationship can be simplified to this, where I've used an average specific heat at constant volume. Likewise, the change in entropy of my ideal gas predicted using the second TDS relationship goes as follows, where in this case I simplified it to such, using the ideal gas law and an average specific heat at constant pressure. So these are based off of average specific heat analysis, right? So a more exact analysis would deal with variable specific heats, right? So not an average. So we can look at the entropy change of an ideal gas using exact analysis. So I still have the ideal gas law, and my first TDS relationship is T ds, I'm using small s, equals d small u plus p d small v. And then for this case, CV equals partial u with respect to t at constant volume, right? For my second TDS relation, I have T ds equals d small h minus v dv. And in this case, I'm using the specific heat at constant pressure. So you notice I use constant volume and I have a dv here, and constant pressure, right? I'm using constant pressure heat capacity. So if you want to remember which one is more useful, well, you can remember that Cp is related to partial h with respect to t, and Cv, so partial h with respect to temperature at constant pressure. Okay, so I can divide by t and integrate, so let's do that. S2 minus S1, so this is the exact analysis of an ideal gas, equals the integral from 1 to 2, Cv, which is now a function of temperature, dt over t. And then the last part comes out to what we already solved for, so we have R gas, natural log of V2 over V1. Likewise, I can do the same thing. S2 minus S1 equals the integral from 1 to 2, Cp, which is a function of temperature, dt over t, minus R gas natural log P2 over P1. So I can just see we have some kind of understanding of what the heat capacity looks like. I have a plot here where now I'm plotting Cp or Cv as a function of temperature. This represents absolute zero. Now, when you do calculations, it's always best to convert to Kelvin units. Okay? Because if I say 0 degrees C, this isn't true. It doesn't do this. It's at 0 Kelvin where the heat capacities approach 0. So when you do any calculations, it's always best to just convert to Kelvin. Turn your Celsius, your Fahrenheit, whatever, into Kelvin units. I guess if you want to stay in the English units, then you can convert it, you know. But I would just say stick with SI. And then if they want to, if you're working for an air conditioning manufacturer and they want to know the BTUs, do that last, right? So I have the specific heat at constant pressure, constant volume, and it looks something like this. The specific heat is 0. And this curve is pretty universal for gases, liquids, and solids. Now, if I take a semiconductor, okay, so doped silicon, which is used for all your computations in your computer, it has a similar curve, but then at some temperature it starts to roll off and start to decrease again. But for this low temperature region, gases, solids, and liquids all look pretty much like this. So I think the thing to remember is the heat capacity of almost everything, well, everything I know of, approaches 0 as you go to absolute 0. So, okay, just as another side note, the heat capacity, so what other property do we know that approaches 0 at absolute 0?
Entropy.
Entropy. How do we define entropy? Options. We had that S equals the natural log of omega, right? KB times the natural log of omega. Omega was the number of options. The number of options are based off of vibrational modes, right? Vibrational modes. Heat capacity is also defined by the vibrational modes of your material. So as you go to one vibrational mode, the natural log, so you can also devise formulas similar to how entropy looks for the heat capacity. But if you're interested, the heat capacity is also dictated by vibrational modes options. So within this curve, there's a linear region. Now, this is 0 Kelvin, right? This is some higher temperature. It always looks like this. 300 Kelvin's room temperature, right? So typically you're going to be dealing with something that, where it looks pretty linear. So if you're in a linear region or your delta T is small, it's very useful to use an average specific heat. So I can call this T2, T1, right? And just say Cp at T1 and Cp at T2. And if my system is operating between T1 and T2 and I want to simplify, get a quick answer, then I just use the average value. So Cp average equals Cp T2 plus Cp T1 divided by 2, so it's just an average value. That works okay in some cases, actually most cases it works okay. And so it definitely works well in cases where Cp, the partial of Cp with respect to T is a constant. Well, that just means my slope on a Cp T curve, right, is constant. So say this is of water, okay? And it looks something like this. And let's just say that temperature T2, say this is water. Forget about this region over here for the time being. So we have water, at atmospheric pressure, and T2 is 100 degrees, 400 degrees Kelvin, okay? Or 373 degrees Kelvin, right? So I know that I'm going to start evaporating, phase transformation. What happens to CP when I go from liquid water phase to vapor water phase? What's that?
Like one part of you is, or your region is vapor.
So what would, just with this, if, how would this part of the curve change if right at T2 I go from liquid, I have a phase transformation?
It would be flat.
Okay, so one is flat. Okay, any other guesses?
Maybe volume.
What's that?
The volume change.
Well, okay, the volume might change. Okay, that's fine. This is the heat capacity though, right? So I could make this a constant volume, right?
Yes.
But let's just, it's better for water to say constant pressure because then I know I'm going to have a phase change at T2, right? 1 atmosphere pressure, constant. So what happens to this curve? Once one of your fellow classmates said, go down, yes. It's discontinuous. So if this is water, this value is on the order of 4 kilojoules per kilogram Kelvin. When I go from liquid, it jumps all the way down to here. So if I want to use an average heat capacity and between two temperatures, T1 and T2, and I know within that I'm going to go from liquid to, I can't say it's this. Because really, it's mainly that. This region. It just turns out as soon as I get here, it drops all the way down. So this is another example of where we use average values. Sometimes when you have different phases, you can't do this average value type thing. You can do volume and mass weighted averages. So just as an example of a volume weighted or mass average, so I can have internal energy of a liquid vapor mixture equals X times the internal energy of the vapor plus 1 minus X, the internal energy of the liquid. This is the mass fraction, right, of vapor. So this is, I could also write it as, I could change X into a volume weighted, right? But so this gives me the average value, right? And so I could do this at one temperature and another temperature, and then I can start doing that. Okay, so this exact analysis, get CP as a function of T from tables. Once you get it from a table, you can put data points on here, and then you integrate with a computer numerically. And then you integrate, but when I say integrate, just like you remember when you calculated in physics and calculus, the average mass, right, or the center of moment, or the mean value of something. So you have CP at T, you can calculate the first moment or the average CP at T when you do it numerically. But okay, so when I say integrate with a computer, you calculate the first moment, or the average, or the first moment means the average heat capacity. But you get data from tables and then you use a computer. Another approach, I say simple, but it's not necessarily conceptually simple, is to define this entropy with this 0 above it, right? And let's define it as the integral of 0 to T, Cp at T. So constant pressure. So recall we use the average value of this to take out the temperature dependence, so our integral was just 1 over T dt, right? Which is a natural log of T2 minus T1, right? Over T1, okay? So we want to do this where we have a temperature dependence where it's not smooth, for example. So one thing they do is they define this S sub 0, and I'll get to what this actually means in a second. And then I want to know the integral from T1 to T2 of Cp of T dt over T. Well, I can break this up into parts, right? I can go from the integral from 0 to T1, or let's T2, Cp of T dt over T, minus the integral from 0 to T1, Cp of T dt over T. So I have an integral from T1 to T2. So if I look back at this curve, this integral, right, represents the area under the curve. So in some ways I should probably plot this as 1 over T instead of T. Right, so then 1 over T2 would be over here, and right, and T1, so the curve would change a little bit. But nevertheless, this is related to an area, right? I guess I wish I'd have known, in hindsight, I wish I would have put 1 over T as the x-axis, and then wrote how Cp looks as a function of 1 over T. But nevertheless, okay, so I have this, it's correlated to the area from T1 to T2, right? From T1 to T2. But if I take the area from, say, T2 to 0, and I subtract the area from T1 to 0, that is going to equal this. So the integral from 0 to T2, of course, should be 1 over T, and the curve would look a little bit different, right? 1 over T at 0 would be infinity, so I'd have something that looked differently, but nevertheless. This minus that. But then I have my earlier definition of S sub 0, so that basically means that this is equal to S20 minus S10. And so using this type of analysis, I can use these values here, right, for my S2 minus S1. So I have S2 minus S1 equals S20 minus S10 minus R gas natural log P2 over P1. Now this and this are only functions of pressure, or this part here is only a function of pressure. And this part is only function or functions of temperature. And are tabulated. See table A17 in the book. So for ideal gas, these values are tabulated, and they represent kind of that integral way of looking at CP. So this was for the second TDS. For the first TDS relationship, I get something similar, but I'm going to put question marks here. Would be a function of temperature at constant volume. this was only, so it would be a function of temperature at constant volume. It turns out that it's not very useful, and or it's not even defined. So for the first TDS relation, I could do the same type of thing, and I'd have something here. I could define some S0 type thing, but it turns out that it's not very useful. So there is no S0 type of way of looking at it. Okay, so I'm just, a lot of this is just to get you guys introduced with the ideas of temperature dependencies of properties and the reason you need to use calculus. So let's do a special case. Special case of TDS analysis, and we'll say constant specific heat, isentropic, and an ideal gas. So constant specific heat means partial a CP with respect to T at, so this is equal to what? Is equal to 0. Isentropic means what? What does it mean to be isentropic? Delta S is equal to 0. So a system is an ideal gas. It's an isentropic process. It's an ideal gas with a constant specific heat. Okay, it's a special case, right? Isentropic, delta S is equal to 0. Ideal gas, PV equals R gas T. So let's go to the first TDS relationship. So I have, again, TDS equals du plus P dV. Second TDS, TDS equals dH minus V dP. From this I can go delta S is equal to the integral from 1 to 2 CV a T over T dt plus R gas natural log V2 over V1. Likewise, ds is equal to the integral from 1 to 2 Cp of T over T dt minus R gas natural log P2 over P1. So of course, when I do this and I do all the integration and all this other stuff, I just use the ideal gas law to get this part simplified, ideal gas law to get this part simplified, and I still have, but now I have Cp and Cv, they're constants, so I can move them outside, right? And I have isentropic, so given I have isentropic, delta S is equal to 0, which equals Cv natural log T2 over T1 plus R gas natural log V2 over V1. Like same idea. Isentropic, delta S is equal to 0. Cp is a constant, comes outside the integral. Cp natural log T2 over T1 minus R gas natural log P2 over P1. So now I can move around, I can move things around, right? And so let's just do that. Natural log T2 over T1 equals, so I'm just gonna take this to this side, right? Or take this to this side and multiply by -1. So I have R gas over Cv natural log V2 over V1 Likewise, I can take this to the side, multiply by -1. So I have natural log T2 over T1 equals R gas over Cp, natural log P2 over P1. Now, when I have a number in front of a natural log, that's equivalent to bringing the natural log to a power. So I get the natural log T2 over T1 equals the natural log V2 over V1 to the minus R gas over CV. And then, of course, this is a minus sign, so that's equivalent to the natural log. And when I have a minus sign in here, making it positive is equivalent to just flipping these around. So I have V1 over V2, R gas over CV, and the same applies here. Natural log T2 over T1 equals the natural log P2 over P1, R gas CV. Now note the gas constant is equal to the heat capacity at constant pressure minus the heat capacity at constant volume. So that's where this gas constant came. So really the gas constant was brought about because people did analysis like this and they wanted to define a gas constant, and so they could measure heat capacities experimentally. So I mean, if you think about how do you measure a gas constant? Well, I mean, I guess I could ask that question in like, how do you measure the heat capacity? But I don't know if you did that in physics, but heat capacity, you add heat, right? So you're adding heat to something, or you're watching how long it retains heat, right? So our gas constant, that's Cp minus Cv. So I can plug this R gas constant into here, or let's just write that out. R gas over Cv equals Cp minus Cv over Cv, which equals Cp over Cv minus 1. And K is equal to Cp over Cv. So this all just gives me K minus 1, which then implies that I have K is equal to minus 1. So let's move up a little bit. So I can again go back up here. I have the natural log of T2 over T1 equals this. But now I've rewritten this in terms of K minus 1, which equals the natural log of V1 over V2, K minus 1. I can just get rid of the natural log type things. So how if I want to get rid of the natural logs in this expression, what do I do? Bring it to the E, right? Exponential. So I can do that, and then it just gives me T1 over T2 equals V1 over V2, K minus 1. I need to keep in mind, so this is T1 over T2, what this bar represents at constant something. So what is it? What is constant?
Pressure. No.
Volume. What else? Remember, it's a special case.
The entropy.
Entropy. I guess I already had it right down here. Oh, I didn't have it quite there. So I have this. I can do the same thing over here, but now I had R gas over Cp. So in this case, it's natural log T2 over T1 equals the natural log of P2 over P1. And then when I go through similar mathematic, just playing around, I have K minus 1 over K. So I get T2 over T1 equals P2 over P1 to the K minus 1 over K. This T2 over T1 is at constant what? Pressure and entropy. So you notice now I have this expression which relates two temperatures of my ideal gas that undergoes an isentropic process with constant specific heats. So I look at it at constant volume. So I could always rearrange this and look at the final. I could just multiply by T1, both sides. So I'd have the final temperature of my ideal gas through an isentropic process, and ideal gas with constant specific heats is equal to its initial temperature T1 times the change in volume, even though I got this from a constant volume process. So you can play around with these things and have special cases. So even though you might not have a constant volume process, you can get an answer by looking at the change in volume. And I can do the same thing here. So let's let T2 over T1 at constant entropy and volume equal T2 over T1 at constant entropy and pressure. So then I get V1 over V2 K minus 1 equals P2 over P1 K minus 1 over K. And what does that give me? So I have all that stuff. I can get rid of K minus 1s. So I get V1 over V2 to the K equals P2 over P1 . So this is related to the ratios of the heat capacities at constant pressure and volume. Ideal gas, isentropic process. Really, the heat capacity is not constant, but maybe it only changes by 2% from T1 to T2. Well, that's pretty much constant, right? If it only changes by 2%. So I get relationships like this. In general, K is a function of temperature, right? So an average value of K can be used. So instead of taking into account the temperature dependence to the heat capacity in some complicated integral analysis, instead I could just look at the tabulated values and take an average value for K and do things like this. Okay? So I can use an average value of K, and I can get various relationships using the ideal gas law, right? So I have this, I can use the ideal gas law, and so I have K minus 1 equals a constant, Tp to the 1 minus K over K equals a constant, or I can do the standard Pv to the K equals a constant. So all of these expressions, constant specific heat, ideal gas, and isentropic, K does not equal 1. So there's a difference between heat capacity at constant pressure and heat capacity at constant volume. So let's just, I have this expression Pv to the K equals a constant. Remember a polytropic process or system? I had Pv to the n is equal to a constant, where n does not equal 1. Delta S equals 0. Which one would it be? Polytropic process Does it equal 0 or does it not equal 0? What is it? It doesn't equal 0, right? Isentropic process. So, polyetropic process where n equals k is equivalent to an isentropic process, right?